Okay, so let's move on. Let me go back to where we were. So this is, I believe, the last slide, the last figure that I showed you. We were looking at the Carnot cycle, and we're going to keep looking at the Carnot cycle today. Remember, the Carnot cycle is an ideal cycle. It's a reversible cycle. But we use it as our comparison cycle when we compare any other real cycle against this ideal Carnot cycle. We can see the difference between real cycle behavior and the ideal cycle behavior. So things to keep in mind, it's a cycle, so the system is undergoing cyclic variations. As any other cycle of this type, it is operating between two temperatures. There is a high temperature and there is a low temperature, and the cycle operates between those two temperatures. And the last thing we did on Tuesday was looked at these Carnot propositions. There's two Carnot propositions, which are two statements that have to do with Carnot cycles. In particular, it's talking about heat engines. A Carnot cycle can run forward and backwards. So if you run it as a reversible cycle, it can go either way. If the Carnot cycle is running forward, then it is a heat engine. It produces power. But if it's running backwards, it consumes power and it works as a refrigerator. So it works both ways. But anyway, if you have a fixed high temperature and a fixed low temperature, so if you take those as fixed, then the first proposition tells you that a Carnot heat engine is the most efficient one between those two temperatures. So if you compare the Carnot cycle to a real cycle, then the Carnot cycle will give you the higher efficiency. And the second one tells you simply that if you have different Carnot cycles operating between two temperatures, they will all have the same efficiency. Obviously, because it's the highest one, it will be the same for all Carnot cycles. So this last, these two propositions actually tell us something, because essentially what it is saying in an indirect way is that the efficiency of a Carnot cycle depends only on the temperatures. Because if you fix the high temperature and you fix the low temperature, then the efficiency of the Carnot cycle is set and is the highest that it can be. So if you think about that, and you think about the efficiency then, we can think of the following. Here's the expression for the efficiency of any heat engine. Right? The efficiency of any heat engine is the net work delivered by the heat engine divided by the heat input to that engine. And if we use the first law of thermodynamics like we did last time, then we can of course write that the net work that comes out of the engine has to be equal to the difference between the heat input and the heat output. So that's from last time. That's for any heat engine. And we can simplify this expression a little bit and write it in this way, which is a little bit more convenient for what we're going to do next. So all I'm doing is dividing by QH. So QH over QH is 1. QL over QH, so I have minus QL over QH. Don't ask me why I wrote it twice. It's the same thing. So, but now we have this that I just told you. For a Carnot heat engine, the efficiency depends only on those two temperatures, on the high temperature and the low temperature. And on the other hand, we have this expression that says that the efficiency is 1 minus QL over QH. So is that the efficiency depends only on QL over QH, but at the same time we're saying that it only depends on TH and TL. And there are many ways in which we could represent that dependence. Because what we're saying is that the ratio of the heat output to the heat input should be some function of the temperatures. And the easiest relationship that you can think of would be to just set it to be proportional. So to say that the ratio of the heat output to the heat input is going to be equal to the ratio of the low temperature to the high temperature. It's a very simple relationship. Later on today, we will actually show, by going through a more elaborate derivation, that this is true for a Carnot cycle. But this is a very powerful relationship. It's only valid for a Carnot cycle. That's why I underlined there in red the word Carnot. This relationship between the heat input and the heat output, the ratio of those two heats, and the ratio of the high and low temperature reservoir, is unique for a Carnot cycle. It doesn't hold for a real cycle, because the efficiency of a real cycle, remember, is always going to be less than the efficiency of a Carnot cycle. But this will be very powerful, and you'll see how we're going to use it when we do some examples. So the bottom line for us is then that we can write that. The efficiency eta of a Carnot heat engine, that's what the CHE subscript stands for, which is equal to 1 minus the ratio of the heat output to the heat input, is also equal to 1 minus the ratio of the low temperature to the high temperature reservoir. Another thing that you have to keep in mind when you use this expression is that those temperatures have to be in absolute degrees. If you plug in this, if you use these relationships with a non-absolute temperature scale like Celsius or Fahrenheit, you will get wrong numbers. That's why the title of this slide, which is now hidden, is absolute temperature scale. Because in a way, this defines an absolute temperature scale. Whether you do it in Kelvin or in Rankine is irrelevant, you'll be the same, but it has to be an absolute scale. Okay, so now if you remember the Kelvin-Planck statement from last time, told us something about the QL. Does anybody remember? The Kelvin-Planck statement is the second law of thermodynamics statement, and it imposes a condition on the QL. Does anybody remember, or can you look it up quickly, what that condition is? Say that again? It can't be equal to zero. So essentially, remember, the Kelvin-Planck statement tells you that you cannot have a heat engine that doesn't have a low temperature reservoir to which it rejects energy. Right? So you could not have a cyclic heat engine that receives heat from a high temperature reservoir, delivers work, and there is no heat rejection. All the heat input goes into work for a cyclic engine. He says that's impossible. So it's what he said. The easiest way to think about that is that the Kelvin-Planck statement is telling us that Q sub L cannot be zero. There will always be a Q sub L, which is why, of course, the efficiency is always less than 100%. It cannot be 100%. You cannot make all of the heat input into work available to you. But because of this correspondence between the ratio of heat transfers and the ratio of temperatures, then it's also telling us that T sub L cannot be zero. And remember, that's an absolute scale. So at the same time, it's telling us that you can never reach a zero level of absolute temperature. And indeed, you can't. We cannot reach a temperature of 0 Kelvin, although we can get very close. We can get very, very, very low, but it will never be exactly 0. Okay, the same thing applies to a refrigeration cycle. So if I do the same thing for a refrigeration cycle, so I go back to the previous notes and pull out the expression for the coefficient of performance of a refrigeration cycle, beta sub R. Remember, is the heat extracted from the cold space divided by the work input. And again, from the first law of thermodynamics, the work input has to be the difference between the Q sub H and the Q sub L. And if you rearrange the expression like I did before, so that you write it as a ratio, so simply take this one and divide by Q sub L. Divide by Q sub L, you get 1 Q sub H over Q sub L minus 1. And then go back and say, well, I know that for a Carnot cycle, the ratio of the heat transfers has to be equal to the ratio of the temperatures. So I can make this substitution. Q sub H over Q sub L is equal to T sub H over T sub H over T sub L, just like we did for the heat engine. So make that substitution in there, and you get this expression that you can find the coefficient of performance of a Carnot refrigerator by simply knowing the temperatures of the low reservoir and the temperature of the high reservoir. So just by making that substitution. So again, keep in mind, this expression is always true because this is the definition, the one on top, Q sub L over W in, or if you simplify the way I did here, this is always true. But if it happens to be a reversible cycle, then you can make the substitution using the ratio of temperatures instead of the ratio of the heat transfers, and then you arrive at that expression there. So we have those equivalent expressions to find whether it is the efficiency of a heat engine or the coefficient of performance of a refrigerator using the temperatures only of the reservoir. And then to make the whole derivation complete, we add the heat pump. And remember, the only difference between the definition of the coefficient of performance of a heat pump and that of a refrigerator is that for the heat pump, we use Q sub H instead of Q sub L for the ratio, because that's what we're interested in. We're looking at something that delivers heat, so it's a heat pump. But there's always the W sub N. So of course the only thing that varies at the end is that for the heat pump it'll be T sub H over T sub H minus T sub L instead of T sub L over T sub H minus T sub L. That's the only difference, because one deals with the high temperature and the other one deals with the low temperature reservoir. Okay, any questions about this? No? Then I have questions for you. So let me get this going here where you get your clickers. A bunch of questions from the last lecture. Okay, so that's the last question from last time. We're not going to do that again. Okay, so are you ready? All right, so the second law of thermodynamics is most closely associated with the property A, energy, B, entropy, C, enthalpy, D, volume, E, none of the above. Which property is the second law of thermodynamics most closely associated with? All right, and that should be an easy one, so I'm going to close it soon. 5, 4, 3, 2, 1. We have an even 200 people here. It means that 47 of you are not here. That is correct for the purple team. Entropy, right? Entropy is the property that is most closely associated with the second law. We haven't studied entropy yet, but I did say this last time. For those of you who answer A, energy, which law is energy associated with? The first law of thermodynamics. And the others are just to fill in the spaces. One could argue that the first law is also associated with enthalpy, but enthalpy is really sometimes referred to as total energy, because remember, enthalpy is the internal energy plus the so-called flow energy or flow work. So enthalpy is really like a more comprehensive form of energy. Okay, so that was the first one. Let's close this and go to the next one. Classical statement of the second law refers to A, a heat engine, B, a refrigeration cycle, C, an open cycle, D, a bicycle, or E, none of the above. Okay, so 5, 4, 3, 2, 1, 0. We have 2 more people this time. We have 202. Okay, who said a bicycle? 3 of you did. Okay, so no, it is not a bicycle. It is a refrigerator. Right? Clausius statement of the second law is a statement that deals with a refrigeration cycle. Right? Remember, the Kelvin-Planck statement that I was talking about a moment ago refers to a heat engine. So the Kelvin-Planck statement is about what type of heat engine you can have and which one you cannot have. And the Clausius statement is about what kind of a refrigeration cycle you cannot have. In particular, what does it say? What does the Clausius statement say about this refrigeration cycle? Somebody over there or here.
You can't take the energy from cold to a high reservoir without doing any work.
Right. You cannot take the energy from the cold reservoir to the hot reservoir without doing it, without putting any work in. I always say that, you cannot have a refrigerator that is not plugged in. So, all right. So let's do another one. If anybody has a question about the questions, just raise your hand. Not during the question, though. A Carnot cycle consists of 4 adiabatic processes, 4 isothermal processes, 4 isometric processes, 4 isobaric processes, or none of the above. All this conversation is going on. Okay, let's close it. 5, 4, 3, 2, 1. We got more people participating, 205. Okay, which one? That is correct. Again, none of the above. What is a Carnot cycle? 2 adiabatic and 2 isothermal. So it's 2 of each. 2 adiabatic, 2 isothermal. I may have one more. Now that you're warm. This one we just went over. The efficiency of a heat pump is defined, and it's not really an efficiency. I should have said the coefficient of performance, but it's equivalent to an efficiency. So the efficiency or the coefficient of performance of a heat pump is defined as, you can just look that up because we just had it. So I'll be much faster on this one. 5, 4, 3, 2, 1. Come on. Finish. All right. That is correct. Purple D. A heat pump, remember, is delivering heat, so you want the Q sub H to the high temperature reservoir divided by the work input. Okay, I believe that's the last one. You wanted more? All right. Any questions? Okay, let's go back then to our Carnot cycle. Let me tell you about some other cycles, some other ideal cycles that you are going to learn about. I'm just going to mention them in this class Of course, we're going to be spending a lot of time talking about Carnot's cycle. Very little about the other, the middle two. We'll do some about refrigeration cycles. But this is so you know about them. You will do probably quite a bit more Brayton cycles and Rankine cycles if you're an ME major in 115. And actually, if you are an AE major, you will probably look at Brayton cycles when you take propulsion, if you're an AE major. So Carnot we have already seen. I note here that these are all reversible. So these are all ideal cycles. The Carnot we have seen, 2 isothermal, 2 adiabatic. Then as you can see, the other three, the Brayton cycle, the Rankine cycle, and a refrigeration cycle, simply replace the 2 isothermal with 2 isobaric. So it's 2 isobaric and 2 adiabatic for the other three. And in fact, the first three are power cycles if they are running forward. Remember, the Carnot cycle, we can run forward or backwards. The Brayton cycle and the Rankine cycle are seen as power cycles, so they are delivering a net amount of work. The refrigeration cycle is the opposite, so it's actually you need to put work in to remove heat from a cold space or to add heat to a hot space. And the only difference between the Brayton and the Rankine, really, because they're both power cycles, is that the Brayton cycle is a gas cycle. So the ideal Brayton cycle, when you start looking at it in detail, you actually do it with air. It's, for example, the cycle in a jet engine. It operates on the Brayton cycle. Of course, the real engine wouldn't be an ideal cycle, it'll be a real cycle, but it'll be based on the Brayton cycle. And the Rankine cycle is actually a liquid vapor. It's the cycle that you see in a power plant that is producing electricity. It operates normally on a Rankine cycle with steam as the water, as the working fluid, going liquid to vapor, back to liquid, and so on. So Brayton cycle uses gas, air, typically, or a mixture of air and fuel. And the Rankine cycle is a liquid vapor cycle. And I also wanted to show you what they look like on property diagrams. For example, if we look at a Brayton cycle, I did both the PV diagram and the TV diagram. So the only thing that you have to keep in mind is what it is. It's always 2 isobaric and 2 adiabatic. So if you do it on the PV diagram, that's an easy one to do because of the fact that 2 of the processes are isobaric. In this case, the process from 1 to 2 is isobaric. It's the one that takes place at a high pressure. And then the process from 3 to 4 is also isobaric, is the one that takes place at the low pressure. And then the other ones in between, from 4 to 1 and from 2 to 3, are adiabatic. So remember, you can also view them as expansions and compressions depending on the volume. And it's easy to see, of course, from 1 to 2 you have an expansion, volume is increasing. From 2 to 3 you still have an expansion. So the whole process from 1 to 3 is an expansion divided into 2 parts. First isobaric, then adiabatic. And then from 3 back to 1 is a compression. First isobaric and then adiabatic. And here's the same cycle, but this time on a TV diagram. And remember, on the TV diagram, the isobars look like that. Always keep in mind where the dome would be. We're talking about a gas cycle, so the dome is all the way to the left side. It's not visible to us. It's irrelevant for our cycle. And so these are the isobars that have come off from the dome and are moving upwards. And therefore, that's my high pressure isobar pH that was here from 1 to 2. It's here from 1 to 2. And then the one from 3 to 4 is down here, Pisabel. So it's the same cycle, but in 2 views. PV view and then the TV view. All right? And that's the Brayton. And then if you look at the Rankine cycle, You might remember at the very beginning of the course, I showed you a video that had to do with a jet engine, and in fact, that engine is running on a real Brayton cycle. Here's a Rankine cycle. So this one is, as I told you earlier, the one you would see in a power plant. It's also 2 isobars and 2 adiabatics. So you can see the isobars here. I only did the TV diagram because I'm going across the dome. Right? So here's my isobar coming up, then going across, and then going up, the one at the high pressure. And here's the one at the low pressure, down here and then across. So if I start from 1, here I have compressed liquid at 1. It goes into the boiler. 1 is the entrance to the boiler. It gets heated. That's where you add heat. That's the Q sub H. And then it boils, and it comes out superheated at 2. Exit of the boiler going into the turbine. It expands through the turbine. That's when it will deliver the work, the W out from 2 to 3. In the ideal Rankine cycle, that is an adiabatic process. Remember, it's 2 isobaric, 2 adiabatic. This one is adiabatic, meaning that you think of that turbine as being insulated. No heat losses from the turbine. Comes out at 3, still as a superheated vapor, but at a much lower pressure. And then it goes into the condenser where you remove the heat, Q sub, I should call it Q sub L instead of Q sub C, so make this an L. The low, to the low temperature reservoir. And then it condenses, so it comes out, in this example, as a saturated liquid at the exit of the condenser. Then it has to be pumped up to the high pressure again, and that's what the pump does. So remember, the pump requires some work, but the amount of work required by the pump should be much less than the work that is delivered by the turbine, so that you actually have a net amount of work delivered to you. That's the Rankine cycle. Any questions for these two? The last one is, in my list, the refrigeration cycle. First thing to notice is that it runs the other way. So usually when you sketch the power cycles, they go clockwise on these diagrams. Now here's a refrigeration cycle, also in a PV diagram. It goes the other way. But again, it's still between 2 isobars and 2 adiabatic lines. So here is my 2 isobars, the high pressure and the low pressure. They are associated with the pressures in the condenser and the evaporator, respectively. So the high pressure is the condenser pressure, the low pressure is the evaporator pressure. So again, if you start from 1, here it's a mixture of liquid and vapor at 1, some quality. Goes into the evaporator where it receives heat, so you might want to add here, this is the Q sub L from the low temperature reservoir, but it's now an input. Comes out of the evaporator in this example as a saturated vapor, then goes into the compressor. The compressor will require work, so you can put that in here. You need to drive this compressor with a certain amount of work. Comes out of the compressor at number 3 as a superheated vapor, and then goes into the condenser, which again is a constant pressure device. 3 to 4 comes out of the condenser as saturated liquid. In the condenser, of course, in order to condense from vapor to liquid, it dumps the heat out to the high temperature reservoir. And then you just need some sort of restriction, an expansion valve, or something that drops the pressure from the exit pressure in the condenser back down to the pressure in the evaporator. So that's what the valve does for you, brings it down. So there you have examples of 3 more cycles. So not only do you have the Carnot cycle, but you have 2 other power cycles, Brayton and Rankine, and then a refrigeration cycle. We'll spend most of the time talking about Carnot cycle, but once in a while this will pop up in examples and problems. Talking about examples and problems, let's do one. Quite a few new concepts between last time and this time, so let's start with a very simple problem. So in this problem, which is, I'm not sure if it's in your homework, I'll double check. Let's see, which homework are you doing now? I don't think it's, you should be doing, which one? You just turned, the one that was due today was 5? Yeah, so, as soon as I learn that the website is up, I will let you know, and I'll just push the window so you can turn in the homework, those of you who were having trouble. So this one, I don't think, oh yeah, it is. This one is in your homework set. So what it is we have a certain heat engine. So let me sketch this for you here. We have a certain heat engine, HE. Think of it as a black box for this simple example. And then this heat engine is receiving the energy supply, the Q sub H, which happens to be given, and is 325 kilojoules, from a reservoir which is at 1,000 Kelvin. All right. Then this heat engine delivers, is operating in a cycle, and delivers a net amount of work, which is 200 kilojoules. And in doing so, it rejects heat to a low temperature reservoir, which is at 400 Kelvin. And the amount of heat that it rejects, Q sub L, is 125 kilojoules. So somebody comes to you and tells you that they have this heat engine, and then you are to review it and tell me or the person whether this is possible or not. Okay? That's the question. All right. Is this possible? So what do? First thing you check is, what should you check first?
First law.
First law. Right? First law. And that's usually pretty easy to check. Does this engine satisfy the first law? What is the answer? Yes. Yes, it's obvious because you can in your head do the energy balance, right? Essentially to check whether QH minus QL is indeed W, and that checks. So first law is fine. All right, so then we check second law. How do we check if this engine satisfies the second law? Yeah, so that part is okay, right? Because so if you think, well, Kelvin Planck's statement tells me that such an engine must have a heat rejection process, and indeed it does. It has a heat rejection process. So it's okay as far as the Kelvin Planck statement, but that's not the only thing you need to check.
QH can't equal W. QH cannot equal W.
QH cannot, well, but that's checked. That's the same thing, right? So QH is not equal to W because there is a QL. So that part of the second law, the Kelvin-Planck statement, is satisfied. So far so good. But is there something else that we need to check? Let me go back here to one figure that we looked at today. For a given TH, the first one in particular, for a given TH and TL, a reversible engine is more efficient than an irreversible heat engine. Presumably, our engine is a real engine. Right? This presumably, we don't know for sure, but it's a real engine, real numbers. But the first proposition tells us that if I compare my engine, which is a real engine, with the ideal one, which would be a Carnot engine, the Carnot engine should have the higher efficiency of the two. Right? So can I find, for example, what the Carnot efficiency would be in this situation? The efficiency in general, for any engine, we know it's W over Q sub H. That's true for any engine. So I can go ahead and compute this because I have all these quantities. So I do 200 over 325. And I can get a number. Do I have that? I'm not sure. Yeah, I think that's the 0.615. That should be what this is. This is 0.615. Yeah, 2/3 would be 0.666, so it's a little less. So I have that ratio, yes.
Is this a Carnot cycle, or do you not know?
We do not know. But we know that the efficiency of this engine is 61.5%. Right? The question is, what if I replace this engine with a Carnot engine? What would be the efficiency of a Carnot heat engine in this problem?
0.4.
Huh?
0.4.
Is that what it comes out to be? It would be, remember, is 1, from what we just saw, minus TL over TH, right? Because we saw that there is a relationship between the heat transfer ratios and the temperature ratios if it's Carnot. So if I do this, then what do we get? 1 minus 4.4, right? So 0.6. So this is, let me just put all the numbers in here, 400 over 1,000. So this is 0.6. So now we can answer the question. Is this engine possible? No. The answer is no, because this heat engine, as described, has an efficiency that is higher than a Carnot heat engine operating between those two temperatures, and that's impossible. So the answer then is no. It's not possible. Suppose that we had gotten for the two efficiencies exactly the same number. Then so would you say that it's possible or not?
No.
No, it's still impossible because that would be the maximum. That would be if it's ideal, but it's, there's no such a thing. So if you get the same number, all you're saying is, well, that heat engine is behaving exactly like a Carnot engine, and I know that's not possible because that would be my maximum boundary, but it's a boundary that I cannot reach. Right? So the only possible heat engine would be one that has an efficiency that is less than 0.6.
What if you use the other statement, the one that says 1 minus QL over QH?
You get 0.615. Right?
It's a little bit bigger than that.
Shouldn't be, because then we would be violating the first law. Right? I think what you're saying is if I just replace this W with QH minus QL. Use what?
For the Carnot one, use 1 minus QL over QH.
Then you would get this. Then you would get the real one, right? But that wouldn't be the Carnot. That would be the real one, right? Because remember, the Carnot one is the only time that you can make the substitution. You can only do this, QL over QH equals TL over TH. You can only do that for a Carnot engine. You cannot do it for a real engine. So I make the substitution. That's what this is. This is 1 minus QL over QH. But I am replacing it for the Carnot heat engine with TL over TH. Right? The Carnot heat engine would have different QLs. So if you fix the QH, the Carnot heat engine will have a different QL. I think that's what's confusing you. So, so if I hook up a real heat engine, a Carnot heat engine in here, and I keep the same Q sub H, it'll have a different Q sub L. Any other questions about this problem? Or any other confusions? Okay, let me see. I got a few things that I want to do here. Let's do a more complicated problem. So, and you do have a similar one in the homework. It's not exactly this one, but here is the situation. It's a little bit more complicated, as you can see. All right, it's from the text. It's 5104. Here's what's happening. The goal of the device that we're trying to design is to maintain this refrigerated space down here at minus 30 Celsius. So we want to keep this space at minus 30 Celsius. In order for us to do that, we're going to put a refrigeration cycle there. And this refrigeration cycle is going to remove heat from the refrigerated space. I'm going to call that Q sub L. And it's going to dump heat into some ambient reservoir that is at 30 Celsius. All right? And I call that heat that I'm dumping in there, I call it Q sub 2. Because I have other heat, so I don't want to call it Q sub H. But it's a Q sub H for this refrigeration cycle anyways. And the way I'm going to do this, of course, I need to drive this refrigeration cycle. And the way I'm going to drive this refrigeration cycle is by using a heat engine. So I'm going to have a heat engine over here that is going to receive energy from a reservoir that is at 200 Celsius. And that's the one I call Q sub H, because that's the highest of the heat transfers from the highest temperature reservoir. So it receives Q sub H from the 200 Celsius reservoir. It delivers work. That's the work that I'm going to use to drive the refrigeration cycle. So the work that comes out of the heat engine W is exactly the W that goes into the refrigeration cycle. And of course, the heat engine will also have to dump heat into ambient. So it's going to dump heat to the same ambient at 30 Celsius. And I'm going to call that Q sub 1. All right? So that's the device or the combination of devices that we're dealing with. And what we're told is that to make our life easier, we're going to think of all of these devices, all of these processes as reversible. So it's an ideal situation. Everything is reversible. Everything is Carnot. And we want to find out the ratio of the Q sub H up here to the Q sub L down here. So in a way, we're trying to determine how much heat do I need to put into my heat engine to remove whatever heat I want to remove from the cold space, which is the Q sub L. So how much will it cost me per, say, kilowatt of energy that I'm removing from the cold space? That's the problem. Okay, so how do we do this? Any ideas? How to get started? Could I, for example, find the efficiency of this heat engine. Remember, it's a Carnot heat engine. If it's a Carnot heat engine, all I need to know to find the efficiency is the temperatures of the reservoir, and I have them. I have the temperatures of all the reservoirs, which is nice. So I can find the efficiency of this heat engine. And could I find the coefficient of performance of this refrigerator? Yes, again, because it's a Carnot refrigerator and I have the temperatures. So I can do those two things. So let's do that. So take the heat engine, right? Find its efficiency, W over Q sub H. But remember, W from the first law is Q sub H minus Q sub 1. Right? Here's where you have to be careful with the notation, because I'm calling Q sub 1 the heat rejected by the heat engine. So it's Q sub H minus Q sub 1 over Q sub H, or 1 minus Q sub 1 over Q sub H, which we have seen before. And of course, because it is Carnot, I can go the next step and replace Q1 divided by QH with T of the ambient reservoir with T of the high temperature reservoir. So this last substitution from this line to this line is only possible because it is a Carnot heat engine. And like we said, since we have the temperatures, I can get that number. Again, warning, the temperature has to be absolute. So TA has to be, it was 30, so plus 273, TH was 200 plus 273. So there is my efficiency. I have the efficiency of the heat engine. And since I have that efficiency now, I can just, for example, write the work. Right? The work will be 0.36 times Q sub H. So now I have a relationship between the work that comes out of the heat engine and the heat that comes from the high temperature reservoir. Now I'll go to the refrigerator and do the same thing. The coefficient of performance of your refrigerator, beta sub R, is Q sub L over W by definition. Make the substitution that W is Q2 minus QL. Remember, where is the Q2 is the heat rejected by the refrigerator. So Q2 minus QL has to be equal to this work that comes in. So Q2 minus QL. Make it the ratio again, dividing by Q sub L. So you have the Q2 over Q sub L. And because it is a Carnot refrigerator, you can again replace Q2 over Q sub L with the temperatures, making sure that you put them in absolute degrees. Those are 30 and minus 30, because those are these two temperatures, 30 and minus 30. So 30 plus 273 minus 30 plus 273, then you get that number. Coefficient of performance of that refrigerator is 4.05. All right. And of course, then I can write that the work that I need to put into the refrigerator is QL over 4.05. And I'm pretty much then done with the problem, right? Because now I have two expressions for the work, but I told you that the work is the same. The work that comes out of the heat engine is the work that I put into the refrigerator, so these two are the same. If I just set them equal to each other, I can get the ratio that I was asked to get, which was QH over QL. Okay? So if you just solve by setting them equal to each other, you find that the ratio of QH over QL is 0.685. So that means that for every, say, kilowatt of power that you remove from here, you will need to spend 0.685 kilowatts feeding the heat engine. That's the price of running the operation. All right? That's a little bit more elaborate. Any questions? Okay, so let me now do a formal derivation of precisely this kind of a relationship. Okay. I told you earlier that because of the Carnot proposition that says that the efficiency of a Carnot heat engine depends only on the temperature of the reservoir, and the simplest relationship that we can find between the heat transfers and the temperatures is this, where we just take the ratio of the Q's is the ratio of the T's. But now we can formally do it by looking at the details of a Carnot cycle. So here is the Carnot cycle that I want to look at. I'm going to take the Carnot cycle of an ideal gas. We saw this figure earlier. Carnot cycle of an ideal gas. I show the two isotherms. I made the high temperature isotherm in red, T sub H, and the low temperature isotherm T sub L in blue. And then my process is there. Remember, there's two isothermal processes and two adiabatic processes. So which are which? 1 to 2 is adiabatic. 2 to 3 is isothermal. That's obvious from the figure. And then 3 to 4 is adiabatic. And then 4 to 1 is isothermal. So that's our cycle, our Carnot cycle. And now we're going to analyze it with some equations. And the only equations really that we're going to use are those two. The first law of thermodynamics and the equation for an ideal gas. All right. So, and I wrote the first law in the so-called, remember, it's for a short segment of a process. So it's in differential form. Instead of writing delta U equals Q12 minus W12, for example, I write it in differentials. But other than that, it's the same. So differential of internal energy, this is all per unit mass. Differential of heat transfer minus differential of work. And the ideal gas law written that way. Okay, so let's go now and analyze process by process. So let's take the first one, 1 to 2. That process is adiabatic. Right? So if I look at the first law, what happens for that process? First law, I'm going to apply it to process 1 to 2. Is adiabatic, what happens? Knock out the delta Q. That's 0. And what else can I do? I know an expression for the work. Because this ideal gas is in a cylinder with a piston. I showed you the picture of this Carnot cycle last time. Maybe it's not a bad idea to bring it back if I can find it quickly. Maybe not. Here it is. Think about this. It's all happening in this cylinder that we were looking at last time. So the one that I'm calling 1 to 2 here is the adiabatic expansion. That is this one here. It doesn't match these numbers, unfortunately, but it's okay. So adiabatic expansion. I'm sorry, it does match. It's the compression, 1 to 2. The volume is going down, so it does match. 1 to 2 adiabatic compression. So it's exactly the same as the figure that I showed you last time. So I can write the differential work, of course, as PdV, because I know that. So I deleted the heat transfer. I put the differential work equal to PdV. And I also use something from when we're looking at ideal gases, that the du is CV dt. That was on the exam, right? The problem of the tank with the membrane. To find the heat transfer, you needed to find the change in U, and most of you did it this way, which is the way to do it. So I know that du is CV dt. So I have this expression that is valid from 1 to 2. Now I'm going to take the ideal gas law. So I'll take this pressure and replace it with RT over V from the ideal gas law. Right? And now move things around to convenient places. So take the temperature and move it to the left side. Leave the volume here, so you get that. Now I have the dt with the t and the dv with the v, which is very convenient because I can now, you might guess, do what? What would be the next step? If you're following. What should I do next? Yep, integrate it, right? So integrate that from 1 to 2, because I'm following that process from 1 to 2. So integrate from 1 to 2, cv dt over t. Of course, when I go from 1 to 2, I'm going from the low temperature to the high temperature. So I can just replace the limits of the integral. Instead of saying 1 to 2, I say TL over TH. And the right-hand side, because happens to be that R is a constant, I can integrate it. And that's the natural log. So I end up with this. This integral from TL to TH cv dt over t is equal to minus R natural log V2 over V1. And I'm going to save that. I'm going to call it 1 and save it, because I'm going to use it later. And now I'm going to take the next process. So that was from 1 to 2. Now I'm going to go from 2 to 3. Right? 2 to 3 is isothermal. Right? So I write the first law, and I do the same substitutions. du is cv dt equals delta Q minus PdV. This time is isothermal, it's not adiabatic. So because it's isothermal, the temperature, I cross it out, the dt. There's no variation in temperature from 2 to 3. So I knock that out. And therefore all I have left is that delta Q is PdV. And if delta Q is PdV, and I now bring the ideal gas law, like I did before. So replace the pressure with RT over V from the ideal gas law. And then, of course, now do an integration. So if you do an integration next, from 2 to 3, the integral delta Q from 2 to 3 is just Q2, 3. And the right-hand side, again, integrates to the natural log, because we are so lucky that the R is constant, but the temperature is also constant, because this is an isothermal process. So temperature is constant, is the TH here from 2 to 3. So I pull that out, and it comes out here. So that's my second expression that I'm going to save. Save that. And let me see. Oh, we got plenty of time. So save that. And then go to the next process. So now we're going to go to the next process, which is the adiabatic process from 3 to 4. So you can see this is going to be very similar to the first one we did, so I can go a little faster. So from 3 to 4 is adiabatic. I write the first law, cross out the heat transfer, replace the du with a cv dt, replace the dw with a pdv, bring in the ideal gas law, nothing different, the same as the first time. Move things around, bring the temperature to the left, leave the volume on the right, do the integration, and now you get that. And of course, the integral from 3 to 4 is the same as the integral from TH to TL. So now I'm integrating, remember I'm going from 3 to 4 here in this plot. So I'm going from TH to TL. But that's not going to be as convenient. It's going to be better to go from TL to TH. But remember, if you switch the limits of an integral, all you do is switch the sign. So if I flip the limits of this last integral, instead of being from T to H to TL, I make it from TL to TH, then I have to switch the sign. But I can also do that by flipping the argument of the natural log. So instead of V4 over V3, I write a V3 over V4, because that also flips the sign. So that's my third expression. It's very similar to the first one. If you compare it to the first one we saved, right? In fact, the left-hand side is the same. Right? Integral from TL to TH of cv dt over t is the same, but the right-hand side is different. So that's my third expression to save. And then the story is coming to an end when we do the last process. which is again isothermal, so it's going to be similar to the second one we did. So if we do it for the isothermal process, first law, it's isothermal, so the dT disappears. Is 0, no variation in temperature. dq then is just PdV. Bring the ideal gas law, RT over V, same as before, and integrate. The integral now is from 4 to 1. And again, the R is a constant and the T is a constant because this process is isothermal. So, but now this is TL. And the integral of dV over V is the natural log V1 over V4. So, that's it. So we got 4 expressions that we arrived at by looking at the 4 processes. All right? So now we're going to start using them. The first one I already told you. If we took the first one here and notice that is the same as the third one, then we set them equal to each other. Because the first one and the third one are the same. So if I do that, first and the third are the same, then I find this nice relationship between the volumes. Because remember, the left-hand side had the integrals of CV dt over t, but the right-hand side had the natural logs. So by just setting the two equal to each other, you find that the volumes are all connected in this way. Volume at 2 divided by volume at 1 is equal to volume at 3 divided by volume at 4. Remember the figure. So these are these 4 volumes, of course. V1, V2, V3, and V4 that you would read on the horizontal axis here. So they are related. And I can write it any way I want. So V2 over V1 equals V3 over V4 is the same as V3 over V2 equals V4 over V1, whichever way is convenient. I can write it either way. All right. So I get that. But now if you think about this relationship between the volumes and you compare the 2 heat transfers, so we got Q41 is that, and look at what we got for Q23. You have it in there. So if you compare now this Q sub 23 to this Q sub 41 and realize that one is the Q sub H and the other one is the Q sub L. Because these heat transfers are the ones that are coming in and coming out. So you can realize that the Q41, you look here at the bottom, is nothing but the minus Q sub L. The reason for the minus sign is because when I do the integration, because I'm going from right to left, I'm going to get a negative value because that's heat that is coming out of the system. So that's why it's negative. So I put the negative sign to make it Q sub L, to just take the absolute value of it. So then you have that the ratio between Q sub L or Q sub L by taking the ratio of the 2 expressions is this, TL over TH times the ratio of these natural logs. But we just showed that these arguments are the same. V3 over V2 is the same as V4 over V1. So the long story ends by just crossing that out. That's equal to 1 is the same. And therefore, Q sub L over Q sub H is TL over TH. And that's a formal proof of what we first said just by saying the simplest possible relationship between the ratio of the Q's and the ratio of the temperatures, if that's all that the efficiency depends upon, is that. But now you show it by using the first law and the ideal gas law, that this ratio is what it is. So I know that's a long and tedious derivation. It's not that hard though, and I'm not concerned with you memorizing how to do a derivation like that, but very important for you to understand how we arrive at it. Let me see, I think I have time to use this. Let's use this in an example. It'll help fix all these ideas. Are there any questions about the derivation itself? Any of the steps? Anything that wasn't clear, you didn't understand? Okay, so let me do this example, which uses all of these concepts. So we have precisely a Carnot air cycle. And if we sketch it just like we had this one, it looked like this. So let's make the cycle here in red. So this is my cycle. All right. All right. On a PV diagram. So PV, here's the TH, here's the TL. And we're given the following data. So it's an air Carnot cycle. Okay. We have the high temperature, TH, is given, is 600 Kelvin. The low temperature, TL, is also given, is 300 Kelvin. The QH is also given, Q sub H, is 250 kilojoules per kilogram. It's a lowercase q sub h, so it's a specific heat transfer rate. That's why it's per kilogram. That's how much heat is added to the cycle. And we're also given the pressure at 4. So let's put the numbers here. 1, 2, 3, and 4. So 4 is the lowest pressure. It doesn't look, well, yeah, it does look like it's lower. So if this is P4 at the very bottom, all right, that pressure is given, P4. And it is 75 kilopascals. Okay? And the problem asks to find V1, P1, and the net amount of work per unit mass. This is lowercase w. All right. Okay. So this is essentially just a straightforward application of what all these equations that we developed. For example, because it is a Carnot cycle, we can immediately say that Q sub H over Q sub L is equal to T sub H over T sub L. That's because it is Carnot. So if not, I couldn't do that, but I'm told it is a Carnot cycle. All right, so, and I have these temperatures, right? And I have the Q sub H. So the only unknown here is the Q sub L. So I can get the Q sub L from here, Q sub L. And if you plug in the numbers, you will get 125. And you have everything else. 125 kilojoules per kilogram. All right? Okay, what else can I do? I can immediately get the work, because it's just an application of the first law. So I can immediately say that W net is going to have to be Q sub H minus Q sub L, just from the first law. It's right here, first law. And I just computed the Q sub L, so Q sub H was 250 minus 125, so it's 125. The last question is answered. All right. So I need to find still V1, P1, and so on. So that's when I can use some of the relationships that we just developed. So in particular, we want one for Q sub L. So we had this one. This is from the derivation a while ago. Here is remember, this is the Q sub L, but this would come out negative because of the way the integration is done from 4 to 1. So this is minus Q sub L. So if I just take that expression and write it here, writing it as minus Q sub L, so I get minus Q sub L is equal to R T sub L natural log of V1 over V4. All right? And what do I know and why do I not know here? I know the T sub L, of course I know R. This is air, so I can get the R for air. So I know the low temperature it was given to me is 300. Q sub L I just calculated. So the question is V1 and V4. And the one that I want, of course, is V1. That means I need to know V4. So I know everything in this expression except for V1 and V4. I can use this to find V1 if I can get V4. But how can I get V4? Use what? And the work? Or, in other words, we're using ideal gas law. Right? So I can get V4 because I know that P4, V4 is our T4. Right? From the ideal gas law. And T4 is, of course, TL. So I know T4, I know R, I know P4, I can get V4. So if I use this to find V4, then I can go back up here to this one and find V1. Yeah. I'll let you finish the details, but you can solve this one for V1. And now we have answered that question for V1. And how do we get P1? Back to the ideal gas law. So I can now write P1, V1 equals RT1. But of course, T1 is, again, TL. And V1 I just got from above. So I can use this expression then to find P1 and finish the problem. Okay, so I got V1, P1, and and W net, which are the three quantities that were asked. Okay, so that's probably enough. Any questions? I'll see you on Tuesday then.